Hello everyone here on the freeCodeCamp channel today. My name is Anya Kubo and I'm a software developer as well as course creator online. In this online course, I'll be talking to you about the differences between the terms SQL and NoSQL when it comes to databases, as well as which kind of database you use, when and why. In this course, we are going to go back to basics and look at what exactly a database is and how it's defined. We're then going to look at database design and why it's important, what a database management system is. We'll then look at relational databases, followed by an SQL crash course. We will then move on to look at non-relational databases, followed by SQL versus NoSQL, as well as the pros and cons of using relational databases versus non-relational ones. We will finish off with some use cases and then a NoSQL crash course. And don't worry, you'll leave this course with a much better idea of when to use what database technology. Before we dive into the types of databases that exist, let's talk about why they matter to your career as a developer. Data is an important part of IT. Without data, computers and even the internet would be a pretty uninteresting place. If you are aiming to become an application or full-stack developer, databases are your friend. The market today pretty much expects fluency with the relational model. But there is an upside here. According to Stack Overflow's recent surveys, NoSQL skills can really help differentiate you from the pack. For example, in their 2021 survey, the top 4 top-paying database salaries were all NoSQL databases: DynamoDB, Elasticsearch, Cassandra, and Redis. So go grab a hot beverage, roll up your sleeves, and let's get started. If you think the range of choices are a little overwhelming now, just wait until you get into the universe of JavaScript programming. So what are we waiting for? Let's get to it. By the way, this course is brought to you by DataStax. If you'd like to follow along with code examples, you can sign up for the DataStax Astro DB free plan in a few clicks. If you want a deep dive into relational and non-relational databases after the course, check out the Intro to SQL course and the Introduction to NoSQL course right here on the freeCodeCamp channel. Now, let's start with taking a moment to go back to basics and talk through what exactly a database is. A database is a systematic collection of data. In the world of computing, this collection of data can be accessed electronically. You can access it electronically to get data, add data, delete data, or update data. Small databases can usually be stored on a file system, on a simple storage device. This can be something like a SD card, a hard drive, or a USB. Larger databases, on the other hand, while in the past on mainframes or beefy individual servers, are usually hosted today on computer clusters or cloud storage. A file system is essentially something that lives on a storage device such as a hard drive. It defines how files are named, stored, and retrieved. For example, imagine you are using your laptop, which is a Mac, and you plug in your storage device or hard drive, which contains data, into your Mac in order to retrieve a file that you put on it. Now, without any kind of file system implemented, your Mac's operating system won't be able to find the data that you are looking for. It would all be a big mess, essentially. File systems bring in order. This is the same for computer clusters, on which large databases are usually hosted on. Now, so far we have looked at the example of one hard drive. But what if you have way more data than we can fit on this tiny little hard drive? What if you need 10 hard drives? What if you need 10 computers or more? This is what a computer cluster is. You are essentially linking a bunch of computers together across a network to work as one. A cluster can be viewed as a single system, or in other words, one computer. Clusters can be grouped together under one control plane, which is what manages connecting all the computers together and the outside communications. Fun fact, the first computer database was Sabre, the airline reservation system. The process for reservations outgrew the paper card system they used, and IBM came up with a new solution in the early 1960s to help scale up operations at American Airlines. So, that is how we can store our databases, so on a file system for small databases and things such as computer clusters for large databases. But what about databases themselves? How are they organized? This is all down to database design. There are many ways a database can be designed. Heck, you could even design your own database if you really wish. All you would need to do is decide on a database model. A database model will determine exactly how you want your data to look, and not only that, but how you want it to interact with other data. For example, you may have a database model that follows the idea of a table. This will mean that all your data has to fit in the structure. Now, if I'm collecting data on how well each student did at a specific subject in terms of grades, then a table would be great. However, what if I also then decide I want to add how much the student enjoyed the subject? Then this table would not work. We would have to redesign our database and perhaps use a different database model. Perhaps a document model would work better. This is why database design is so important and has to be thought of early on in any project. Here are just some examples of database models. As you can see, there's a lot. We will go into the most popular ones like the relational model, document model, wide column and key value model, and how they define the modern database landscape. First off though, let's talk about how developers interact with these databases. A database management system, or DBMS, is a way for us to essentially communicate with our database. Think of it as a layer or interface between the data and our little fingers on the keyboard. It allows us to get existing data, create new data, update data, and delete data from our database. We have our data in our database here, then we have the DBMS, and then we have the end user. Great! Any given database management system may provide one or more models. We'll talk about the multi-model databases briefly at the end. And for this tutorial, we are going to use a cloud database since they all usually provide a free plan or tier and it's much faster than downloading, installing, and configuring it. Then we can just focus on the code and core concepts. I use AstroDB a lot, so I will be using it since it allows me to create different types of NoSQL databases in one place. Then I'm not switching platforms all the time during the course. However, you don't have to use it. There are plenty of other database management systems out there. Some only deal with one type and some are multi-model, which we'll talk about again later on. Here is a list of some popular DBMS you will come across as a developer. Now, I'm going to show you what a typical cloud database experience is like these days. To get started with AstroDB, sign up for free. Just go ahead and do the process of that by clicking on the Sign Up to Try Astro for Free button. Once here, I want you to sign up. I'm going to go ahead and sign in as I've already created an account for this. Wonderful. Here is the dashboard. We are on the free current plan, which is more than enough for research and development work without being prompted for a credit card. So what we're going to have to do is create our first database. Just go ahead and click the button and it will take you to this page. Once on here, let's name our database something. I'm going to call this tutorial as it is for tutorial purposes and the schema name, or as Apache Cassandra calls them, key spaces. Now we're going to create a few key spaces. The first one we create is going to be called wide column as it's going to be for creating a wide column database. Let's go ahead and do that. Now we're going to select a provider and region. Again, I'm just going to choose the one closest to me. So this will be Mumbai, India, and let's go ahead and click create. Next, you'll see this page show up in which we're going to be given all our tokens and necessary things to communicate with our database. So here's what it looks like. Just copy all of this and make sure to keep it somewhere safe for the upcoming tutorial. And go ahead and click on the Go to Database button. Great! At the moment, this is pending. We are going to have to wait for this to be active before we can use it. But as soon as it's active, you will see the status change to active. So great, we know this is active because we can see options such as Connect, SQL, and more in the tabs above. And we have our first key space, which is wide column under the word key spaces below. We could also add more schema or key spaces, as they are called in Cassandra, which we will be doing later. See? Much easier than downloading, installing, and configuring it, just so you can play with some code. Most cloud databases are pretty similar in how to create a database, so you can start coding straight away. Wonderful. Let's move on. Now that we know how to get set up with our DBMS, let's get into talking about the different types of databases we could have. The first thing we are going to look at is the relational database. We are going to do this in order to understand the differences between SQL and NoSQL. But to get to that point, we still have a little bit of knowledge to cover. And what better place to start than looking at the most familiar and most strongly consistent database in my eyes, which is the relational database. As we now know, databases depend on their design and what type of models they use. Relational databases provide a store of related data tables. These tables have a fixed schema, use SQL or the structured query language to manage data and support asset guarantees. In general, RDBMS assumes you can structure your data and trades off the strongest consistency guarantees and ease of use for ensuring consistency with scalability, volume, and availability. There is a great deep dive on how to design a relational database right here on YouTube if you want to learn more. Popular open source examples here are MySQL, Postgres, and MariaDB. The relational database uses that relational model and looks something like this. Kind of a table with columns and rows that are linked together if we wish. Usually, each table has some kind of theme going on, or in other words, entity type, just like we saw with the grades for our students before. In that instance, each row has a student and each column was a class topic. In relational databases, each row has a unique identifier, so we can pick it out. Thanks to this unique identifier, we can now also link these rows or students to other tables, such as this one, with each student's enjoyment level of topic. We can even take this one step further to really clean it up and take out the names of the students and put them in a third table. Now, all the data we want to be linked is linked thanks to the ID number. These links are called foreign keys in relational design. Sounds simple, right? Now, I'm going to show you how to create your own using SQL for creating, clearing, and maintaining databases. I'm going to be showing you how to do this with some slides. SQL, or the Structured Query Language, is a language that became prominent in the late 1970s for managing data in relational database management systems. It's worth noting that while ANSI SQL does indeed define a standard syntax, each RDBMS has some subtle platform-specific considerations. Some of them in the syntax of the code outside the standard ANSI SQL specifications, and some in how the SQL query execution engine functions at runtime. Many also have wholly proprietary extensions for more advanced features. Now, let's see what creating a schema and table in an SQL database is like. Let's try a simple example together. Here is what the syntax for SQL looks like. For example, to create a student table of grades, we would use a statement. This statement is create table. After this statement, we then define what we want to choose to call our table. I'm going to choose to call it student grades. Next, we define our columns. On this occasion, we will define column 1 as the ID, column 2 as the name, column 3 as the subject math, column 4 as the subject art, and column 5 as the subject geography. We also need to define the type that goes into each column. For example, we can have varchar, integer, date, and much more. We are going to define our ID column as taking integers, our name column as varchar, so it takes characters or text. And for the other columns, we are going to put varchar as well, as we want to put 8 out of 10. If you'd like to just put in an 8, however, you could choose to use integers instead. We can also define a primary key. The primary key constraint uniquely identifies each record in a table. In this example, we would want our ID to be that unique identifier. Primary keys must contain unique values and cannot contain null values. Finally, we put in the semicolon to end the statement and press enter. Great. Now that we have defined our table, let's get to putting data into the table that we have just made. To put in data into our table, we use 2 statements, insert into and values. The full statement would look like this. We would use the command insert into, and then we will use whatever we decide to call our table. In this case, it was student grades, and then we will rewrite the column names that we want to put data into. I'm just going to put in all of them. On the next line, I'm going to use the values command to insert data into those columns. And of course, we need a semicolon to end this statement. Inserted 1 line into our database. But how do we actually look at our database? Well, for this, there's a very simple command. We use the command select, followed by a star, which means all, from our table called student grades. Okay, so great. Now let's test it out. For this, I'm going to use the SQL playground on W3 Schools. And all I'm going to do is literally paste in the commands that we wrote before. So we need to create a table first, So here we are creating a table called student grades with an ID, name, math, art, and geography column, as well as defining our primary key and hitting run SQL. Okay, so that has now been added to our database. The next thing we need to do is add in our line. So add in some data. So I'm going to delete this and just use this command. So this is going to insert into student grade. It's going to insert the ID, the name of the student, the math, the art, and geography scores. So let's run that. As you can see, changes have been made to the database. One row has been affected. And now to get the data, well, we use select all from and whatever we called the table, which is student grades. Ta-da! And you will see our table with the ID, the name, the score the student got for maths, art, and geography. Wonderful! So that was a quick crash course about making relational databases using SQL. Let's continue. Now, this is not an SQL tutorial. I'm simply giving you a very quick crash course on how to use it for the purpose of this tutorial. SQL has a lot to offer and is a very well thought out language that takes a while to learn. If you would like to deep dive into the topic after this course, then please do check out some tutorials on this that we have on freeCodeCamp. So we now have a good idea about what a relational database looks like and how we can manage data in it using SQL, the structured query language. But there are also such things as non-relational databases, and there are a few of them. We are not going to look at all of them. We're simply going to look at the three most popular ones. So we are going to look at the wide column database type, the document database type that uses the document model, and the key value database type, which, you guessed it, uses the key value model. All of these non-relational databases are commonly referred to as NoSQL databases. And whilst you might be thinking, so they do not use SQL, the structured query language that we just learnt, you would be totally wrong. NoSQL means not only structured query language, which allows you to use the language or not use it to get the data, and is considered to be an approach to database management. NoSQL's appearance on the scene is noted as somewhere around the 2000s. So if we compare this on a table, you will see here that under SQL, I've put an icon to represent a relational database. As we can use SQL to query relational databases, we now know that we can also use SQL to query some non-relational databases, or at least the ones that offer relational as a secondary database model and an SQL interface anyway. NoSQL uses different query languages for key value, document, and tabular or wide column, and so on. Now, when people look at NoSQL and SQL, they might be tempted to compare the two. But by now, we know we can't do this. Why? This is because SQL is a database management approach and SQL is a query language. So two completely different things. It might be better going forward to start referring to NoSQL databases as non-relational databases. So let's go ahead and switch that so we can compare them to relational databases from now on. Okay, great. So now that we have that down, let's look at the pros and cons of each. First off, let's look at standardized schema. When working with relational databases, you can have the benefit of schema being standardized. For example, imagine I'm working at a pizza restaurant as a chef, and each waiter, instead of showing people menus for people to pick from, started just asking them what kind of pizza they want. You would have a huge range of pizzas to make, and this would add some level of difficulty to your job. In this scenario, the menu is built using a pizza schema. It comes with a list of well-known pizzas that people can pick and you can make. It's the same with data and relational databases. By providing a schema that everyone's familiar with and used to using, it makes working with relational databases worldwide a whole lot easier. Now, some people might find this rigidity a con, but in general, it's viewed upon favorably. Next up, let's look at large user communities. Another pro we have is that relational query languages such as SQL have a larger user community. As SQL has been around for nearly 50 years, it has a strong community of supporters as well as a lot of help and resources out there for learning purposes. Next up is standardized query language. Another pro for relational query languages such as SQL is that it's considered to be quite an easy language to learn as it uses simple keywords. We use these keywords in managing and searching through databases. Anyone that's worked with spreadsheets can relate to this model as it's often covered in university courses. Next up we have ACID. The final pro we have for relational databases is that they tend to be ACID compliant, which stands for atomicity, consistency, isolation, and durability. You will see this acronym pop up a lot. This level of compliance keeps tables in sync and guarantees the validity of transactions. Now, let's look at the cons of relational databases. First up is difficulty clustering. The main cons of traditional databases are that they tend to scale up vertically. What this means is that the only way to scale your database is to increase your RAM, CPU, or SSD on your existing server, or to migrate to a larger, more expensive one altogether. You'll need to continually increase hard drive space as your data grows, and you'll need faster machines to run evolving and more sophisticated technologies. The database vendor you'll use will likely require you to periodically level up your hardware just to run their latest releases. In this environment, hardware can quickly become outdated. Each upgrade is expensive and resource intensive. Most relational database hardware also needs ongoing everyday maintenance. Next up is data normalization. Developed at a time when the cost of data storage was high, relational databases such as SQL ones attempted to negate the data duplication. Each table has different information and they can be connected and queried using common values. However, as these databases get large, the lookups and joins required between numerous tables can slow things down and be too complex to code and debug. Next up is schema first. SQL relational database schemas must be defined before use. Once in place, they are inflexible, and modifications are typically difficult and have a wide blast radius, affecting both data and application. Non-relational databases vary in this respect. For example, document databases do not require schema up front, while they say wide column does. For that reason, substantial time needs to be invested in upfront planning before the database is ever put into production. So it follows that they're only appropriate when all your data is also structured and you don't expect much change either in volume or data type. Next up is resource-intensive scaling. As mentioned earlier, relational databases normally scale vertically by assigning more resources to the existing hardware investment. This can be expensive and time-consuming. Newer relational databases, or cloud services, aka NoSQL, can horizontally scale a relational SQL database through partitioning or sharding. Make sure to understand how the addition of partitioning or sharding for RDBMS affects ACID consistency guarantees, as it can be different from non-clustered deployments. Remember that all RDBMS, or Relational Database Management Systems, are subject to the limitations of CAP theorem the moment a network link is introduced. Now that we have covered the pros and cons of relational databases, let's look at the pros and cons of non-relational databases. First up is continuous availability. With non-relational databases, data is distributed across multiple servers and regions, so there is no single point of failure. As a result, non-relational databases are designed to be more stable and resilient with continuous availability and zero downtime, particularly with cloud deployments. Next up is query speed. Non-relational databases are denormalized without worry or data duplication. For example, in wide column databases, the information needed for a particular query will often be stored together. No joins required. This makes lookups easier, especially when working with large data volumes. It also means non-relational databases can be very fast for primary key or indexed queries. For data without an index, however, query speed can taper off as non-relational databases reach high levels of scale without the right data model. Next up is agility. Non-relational databases were developed as large data storage costs were beginning to drastically drop and systems were being distributed and or deployed on the cloud. Data duplication was no longer a concern. Non-relational schema are generally designed to give the developers more control over database integrity and schema, as well as trade-offs between consistency, availability, and performance. There are a variety of different non-relational approaches. ACID-compliant databases hide the complexity of a very costly operation and give you no other choices with the approach to trading off consistency for performance. Also, there are times where all those guarantees of the relational model simply aren't truly needed. Most developers have been conditioned to reach for the high data integrity relational model without challenging themselves to think deeply about where those guarantees are truly needed. However, understanding the data model now and in the future is arguably the most important thing, so future business requirements continue to align with the strengths of the approach you've chosen. Agility comes in other forms as well. For example, document databases don't have to have predefined schemas. Instead, they are dynamic with the ability to handle all types of data, including structured, semi-structured, unstructured, and polymorphic data. You can skip upfront database schema definitions and get right to development. Developers can redefine JSON document structure anytime and easily add data types and fields at runtime without requiring a schema change. All of this makes the NoSQL approach a great fit for modern agile development teams. The flexibility and adaptive nature of non-relational databases makes them a great fit for organizations that have a variety of data types and expect to continuously add new features and functionality. Non-relational databases are not one-size-fits-all. Unlike the relational databases, they aren't constrained to a single normalized data model, a single approach to consistency, or single approach indexing in their quest for scalability and availability at scale. Next up, we have low cost. Non-relational databases scale out horizontally, making it cost-effective to expand capacity. Rather than upgrading expensive hardware, they can cheaply expand by simply adding commodity service or cloud instances. Open source non-relational databases provide affordable options for many organizations. They are a good fit for cloud computing and handle extremely large and quickly growing datasets. Now, let's move on to the cons. Next up is no standardized query language. There isn't a standard language to conduct NoSQL queries. Some, like key-value databases, are so simple they don't need one. Other NoSQL systems even provide direct support for ANSI SQL. The syntax used to query data varies for the different types of non-relational databases. But unlike relational databases where there is just one easy-to-learn language to master, NoSQL has a steeper learning curve. Sure, each relational SQL execution engine does certain things a little differently, has proprietary extensions and so on, but at least syntactically, they all have the ANSI SQL standard syntax in common. For example, it might be difficult for a developer to quickly get up to speed working on a wide column database if all their prior experience, for example, consists of building and managing graph databases. However, there is an emerging trend to start exposing databases as de facto or popular APIs. It's a helpful alternative for many developers who are able to trade off some level of performance for developer productivity. Using database API gateways saves on you hard coding what would have otherwise been boilerplate data access code. Also, using APIs like REST, GraphQL, JSON, gRPC may already be familiar to many app developers, overcoming some concerns here about standardization. Next up, we have the smaller user community. Developers have been using non-relational databases or NoSQL databases for more than a decade, and the community is growing quickly. However, it's still less mature than the SQL community, so it could be harder to solve undocumented issues. There are also fewer consultants and experts on the NoSQL side. Next up, let's look at developer skills required. Flexibility comes with a price. With the variety of approaches found in non-relational databases, there's more to learn. This, as we know, is unlike learning how to use SQL, which is relatively simple. Even the simplest of NoSQL queries will still likely require programming experience, or possibly to learn an API. This means more technical and costly staff like developers or data scientists will need to perform the queries. Next up is data retrieval inconsistency. The distributed nature of non-relational databases enable data to be available faster. However, it can also make it more difficult to ensure the data is always consistent. Queries might not always return updated data, and it's possible to receive inaccurate information. With its distributed approach, the database could return different values at the same time depending on which server happens to be queried. This is one of the reasons some non-relational databases don't achieve ACID level compliance. Consistency is the C in ACID, which states that data must be valid and consistent at the start and end of a transaction. Instead, most non-relational databases adhere to base consistency models, where the E stands for eventual consistency. In other words, the data will be consistent at some point later on. Different non-relational databases vary in their approaches to consistency and transactions, so it's difficult to generalize. In the real world, this is often a very small delay, only of a few milliseconds, so for many applications, that likely won't matter. For example, social media posts going live or an online shopping cart being updated, that won't really matter too much. In those situations, lower latency and high availability outweighs the value of providing the exact same data at the exact time to users. However, think of when you make an online stock purchase. Then it would really matter. Non-relational databases value speed and availability over consistency compared to relational databases. Each project must decide if that aligns with their goals. Now that we have covered that, it's time for a quick crash course in learning about some non-relational databases. For a full tutorial on NoSQL, check out the Intro to NoSQL right here on freeCodeCamp. Our quick crash course will include looking at the document database type, the key value database type, and the wide column database type. So let's do it. The first one we're going to look at is the wide column database type. Now, as AstraDB is built on Apache Cassandra, we're actually going to be using CQL, or the Cassandra query language, to demonstrate some of the different approaches to NoSQL. The CQL query language is a subset of SQL, so the basic commands we're using here in this video are exactly the same. Okay, so just so we understand, we are going to be using CQL, the query language, which is very similar to SQL. However, we're going to be using it to create a non-relational database. And on this occasion, the non-relational database we will be using is a wide column database. Okay, sounds confusing? Don't worry, we're going to go into this in a lot more detail coming up. When approaching your database's choices in general, it's helpful to understand the models for the concepts behind them that you like to use as points of comparison. Carnegie Mellon's database of databases provides an excellent, much comprehensive technical resource in this regard. But pragmatically, here's a few important aspects for comparing DBMS. In the spectrum of non-relational databases, wide column, aka column family, is sort of in the middle of a spectrum with relational databases on one side and key value on the other. On one side, you have RDBMS, or Relational Database Management System, and ACID DBMS with lots of built-in features and performance overhead, to the much more simplistic, less feature-rich, but way faster DBMS like key value. Popular open source options here include Apache Cassandra, Apache HBase, and many others. They are often used for operational app database tasks like scaling time series data, e-commerce or inventory management, content management, personalization, recommendations, fraud detection, transaction logging, tracking, and many other write-intensive, infrequent update use cases. Wide column stores like Apache Cassandra use the notion of column families, a database object that contains multiple columns of related data that are used together, similar to traditional relational database management tables. Within a given column family, all data is stored in a row-by-row fashion, such as the columns for a given row are stored together, rather than each column being stored separately. Put another way, a column family is a key-value pair, where the key is mapped to a value that is a set of columns. In analogy with the relational databases, a column family is a table, each key-value pair being a row. For developers, wide column tables can present themselves as a row and column table that is familiar and easy to work with in code or APIs. Understanding how the primary key in wide column databases is different from relational primary keys is essential, followed by proficiency in data modeling. To learn more about both of these, I recommend this course in Apache Cassandra as an example. So, using Apache Cassandra as an example, the two biggest differences between wide column databases and relational databases are: wide column has partition and clustering keys. Relational uses foreign keys. Recently, wide column databases are evolving, allowing the ability to provide relational style, secondary indexes for columns outside, and even full ACID transactions, so the spectrum we just spoke about is changing over time. Learn more about these secondary indexes right here on YouTube in the link showing up. So, to look at this in code, CQL or Cassandra Query Language is a subset of ANSI SQL. To compare them, this is CQL select syntax using EBNF notation. It is a subset of SQL. SQL also supports binary operators such as inner, outer, joins, union, except, intersect, nested, subqueries, and clause having. In addition, CQL restricts what columns can be used in different clauses. This is the CQL create table syntax using EBNF notation. We can learn some more CQL basics right here on YouTube following the link popping up. Okay, so here we go. Let's create some tables that store data. So in order to do this, I'm just going to click the CQL tab up here, which will bring up our CQL console. Wonderful. Now, just to check this works, I'm just going to write show host, and that should show us our host. And next, if you want to check the version, I'm just going to type the commands show version, and then follow it with a semicolon to finish off this statement and hit enter. Now, any version will support what we've shown here in the tutorial, since we're just showing straightforward basic syntax. New commands may be available in newer versions, so it might be worth checking what version of CQL you are using. Now, the first thing I want to do is just list out all the key spaces that we have in this database. So to do this, I'm going to use the DESC command for describe key spaces and just hit semicolon again, and that will run that statement and it will bring up all the key spaces that we have in our database. So as you can see, the wide column key space that we made earlier is here. This is the one that we want to use for this part of the tutorial. So we need to go into this key space. Now we can do so using another command, which is the use command, followed by the key space name, which in this case is wide column. Follow it off with a semicolon to finish this statement and hit enter. So as you will see, we are now in the wide column key space. Great. So once again, this is the key space we made previously, and that's what we are in now. Now, once here, it's time for us to start, you guessed it, creating some data, creating a table to put in this key space. So to do this, you guessed it, we're going to use the create table command as we saw previously as part of the SQL tutorial, but we're also going to put if not exists. So if that table does not exist, I want to create a table. And what should we call our table? Well, I'm going to call it pizzas. So that is what I have chosen to call my table. Next up, we need to actually define the columns and data types that make up our table. So let's get up our parenthesis. And I'm just going to hit enter to start this on a new line so it's more readable. And our first column, well, let's go ahead and call that something. I'm going to call it pizza ID, as this is going to store the pizza ID of my pizza. And the data type for this, I'm going to choose to use the data type UUID, which is a data type that comes with CQL. Great. And next, the other column is for the brand of pizza that we're going to have. So once again, let's call our column something, which in this case is going to be brand. And I'm going to define the data type to be text. So in CQL, we can just write the word text like so to say that anything in this column must only be text. Great. On to the next column. The next column, well, I just want to store the actual name of the pizza. So let's go ahead and call our column name. And once again, the data set for this is just going to be some text. So let's go ahead and define that. Next up, I'm going to show you how to work with an array of things. So for this, we're going to have an ingredients column. Let's go ahead and call that ingredients. And then if I want to say that I want to only take text, but multiple texts, I am going to use the set keyword to do this. So we're going to use set, and then using these brackets, I'm going to put in some text. So what I am saying is that the ingredients column will only take an array of texts. Great. So that's another data type that we have just learned. And next, well, we are actually going to want to define how we search for rows in our pizzas table. And I'm going to say that we are going to be able to search for the pizzas by their pizza ID. And to do this, we need a primary key. So I'm going to use the primary key command and just pass through the pizza ID into parentheses to make sure that our table knows that this is the value we can search our tables by. That will bring back the whole row. Great. And of course, finish off the statement with a semicolon and just hit enter. So wonderful. We have just defined our pizzas table. Let's just check that has worked. So I'm going to use the DESC command, followed by the key space command, and then the key space we want to describe. And then we just finish this off, and wonderful. So there we can see how we have defined our table that is working. The next thing I want to do is, of course, start putting stuff into the table. So let's carry on. Now, to start putting stuff into the table, we're going to have to use the command insert into. So let's go ahead and use the insert into command. And of course, we want to insert something into the pizzas table. So let's get that up. And actually, we are going to have to tell this console exactly which columns that we want to put stuff into. So I'm just going to pick all of them. I'm going to pick the pizza ID column, the brand column, the name column, and of course the ingredients column, and not finish this off yet. I'm just going to create a new line so it's more readable. We are next going to use the values keyword in order to insert values into those columns. Now, we can, of course, write our own unique identifier, or we can use a function. So I'm going to use a function for this, and it will randomly generate a UUID for us. So I'm just going to use the function UUID and call it. Next up, well, we know that the brand column only takes strings or text. So I'm just going to go ahead and put in the string of Etkes as the brand. The name is going to be a pineapple pizza. So once again, we need to specify this as a string, as we have said that this column takes text. And next up, we need the ingredients. So to put in the ingredients, I'm just going to get up some curly braces this time and make sure that everything we put in here is separated by commas and is text. So once again, we need to make sure that they are strings. So I've just put in pineapple, cheese, and ham. And now we can finish off this statement. Great. Now let's check if that has worked. To check if this has worked, I'm going to use another command, yet another command, and this time it is select. So I'm going to select all. This star means all. I'm going to select all from the table that we called pizzas. And then, you guessed it, finish this off with a semicolon. And that will bring up our table with the data. As you will see, a unique identifier has been generated for us. It's in green. This is also the primary key, okay, as we did specify that when we were describing our table. And of course, we've got the brand, we've got the ingredients, and we have the pizza name. Wonderful. Shall we put in something else into our table? I think we should. So to do this, I'm actually just going to press the up button. This will bring up the last commands that we wrote, and I'm just going to get the insert into command up. And all I'm going to do is just switch out some of the values. So we are going to switch out the brand of the pizza, and I'm going to switch that out to be Pizza Hut. Again, making sure that that is a string. Of course, we can leave the UUID function as it was. That will generate a new unique identifier for us. The next thing we need to do is change the pizza name. So I'm going to change this to be barbecue pizza, just like so. And on the ingredients, I'm just going to switch these up too, so we can have a few different while keeping maybe one the same. So beef and barbecue sauce. Great. So let's check that has worked. Once again, I'm just going to press the up command to select all from pizzas. And ta-da! we can now see two. We can see two pizzas in our table. This is looking wonderful. Now, before moving on, I just want to put one last row in, so just bear with me. Once again, I'm just going to press the up button so that we can get up the command that inserts into the table pizzas. And once again, I'm going to keep the UUID function there so it can generate a new unique identifier for us. I'm going to change the brand name of the pizza to make it another notable pizza brand. This time is Ristorante. I'm also going to change the name of the pizza this time to be a broccoli pizza for all of you broccoli fans out there. And of course, in the ingredients, we are going to have to put some broccoli in there. We're also going to put some mozzarella, and let's also put some corn. Okay, so lovely pizza. Make sure that is all strings and hit enter. So now if we get the select all from pizzas command, we will see 3 pizzas in there. Wonderful. That's a lot more for us to work with. Let's move on. Now, I can write a command that will select a certain pizza from the table based on the ID. And to do this, we are going to use the select all from pizzas command. So select all from pizzas, but we're not going to use the semicolon. We're not going to finish this off quite yet. Let's make a new line. I'm going to use the where command. So where is another command where the pizza ID, so we're getting the column name, equals the ID of, well, if we want this pizza right here, the pineapple pizza to come back to us, so the whole row to come back to us, I would just simply grab the unique identifier and hit enter after the semicolon, and that will bring back just the pineapple pizza in our table. Okay, so if you ever need to just get one row from your table, that is how to do it using the where command, just like we did previously. Great. Okay, so that was a quick crash course in SQL. Please do not feel fooled. As I said, there are so many other commands you can do. You can become really complex with these commands. Here are just a few to your disposal. We are not going to go into this. As I said at the beginning of this tutorial, this is just a basic overview. So you get the idea between writing relational databases with SQL and making a wide column non-relational database with SQL. There are plenty of courses on both of these languages on freeCodeCamp, so if you want to take things a step further, please refer back to the beginning of this course for the video you need to watch. Now, the next non-relational database type we're going to look at is the document database type. Document databases are popular with mobile apps, content management, games, some IoT scenarios, anywhere where you aren't quite sure how your data is going to be structured. They don't require joins as they use hierarchical collections of denormalized data where fields can be indexed. Popular open source options here are things like MongoDB, Couchbase, and CouchDB. So, wait, I don't have to decide how my data is going to be structured? That sounds great. So why wouldn't I use that all the time? For everything? Well, ideally data should be as structured as it can be. You will pay a price down the road when you want to join it, troubleshoot data type conversion errors, and so on. More strongly typed data and data modeling better defines your app to database interactions, which lower overall cost. For example, data modeling consumes a fraction of the overall developer time in a project and can have a large impact on code quality. Data modeling catches errors and oversights early when they are easy to fix. This is better than fixing errors once the software has been written or worse yet is in customer hands. However, document or document-oriented database types are arguably the easiest types to deal with from the perspective of development because they require no schema. In contrast to models like relational and wide column that require schema before they can be used by an application developer. Before, in the table we made, so in other words, the wide column database, we had to define the column that made up our table as part of that upfront schema definition process. With document databases, we don't have to do any of that. As long as our data comes as an object, it's fine. The objects are made up of keys and values and look like this. This is an example of perhaps an item you might find on a to-do list. The values can be strings, numbers, booleans, arrays, or even objects themselves. This is called JSON, or JavaScript Object Notation, and is the most popular format for document database types. Now, a group of documents is called a collection. We will not be using the word tables anymore. It has now been replaced by collections. Keep that in mind moving forward. Now, what are we waiting for? Let's get to it. In this next section, I'm going to make a collection of pizzas using the document API. But why not a query language? Well, using API like REST, GraphQL, or JSON may already be familiar to many app developers, so it reduces some of the learning curve. Now, for those of you who haven't heard of the term API, let's do a quick crash course. An API stands for Application Programming Interface. They allow developers to enable technologies to essentially talk with each other and are essential to so many automated services that we rely on today. They are behind most apps that we use on a day-to-day basis and can shape the information passed between one technology to another. They can even connect things such as our cars, fridges, or pens to the internet. APIs are everywhere. As a developer, you might use the Twitter API to get live tweets on your site, a map API that will allow us to get data from a third party to use in our new delivery app we are building, or even use them in a two-way stream to get, post, or delete data from a customer relationship management system, for example. There's a reason why these words are popping up, and let's go into why. In this next section, you are going to be seeing these words and using them to communicate with the database you make. In this context, they are called HTTP request methods. The most common are the GET request, POST request, PUT request, and DELETE request. There are others too, but for the sake of the tutorial, these are the ones you need to know. GET essentially gets data, and that's it. So imagine you have a client, or in other words, your computer, and a server. You are on your computer, and the URL, which is where you want to get your data from, is on a server. The client, so once again, your computer, sends an HTTP GET request to the server to retrieve the data we want. So here we have a GET request, or a visualization of a GET request. The client is requesting that the server gives it the necessary resources that we need. Then after the server has sent the response, so request and response, we say that we've got it. Thank you. After the server sends the response, it closes something called a TCP, or Transmission Control Protocol, connection. We also have POST requests and PUT requests. So here we have a visualization of how the requests would work with POST requests, so simply sending something to the server, and with PUT requests, which are the same. We are sending something to the server. But essentially, with the PUT request, we are sending something to edit something that already exists, or in other words, overwrite it. And of course, we also have the delete request, which will delete an existing piece of data on the server. So to get interacting with our data, you will see these different endpoints. Simply put, an endpoint is where a resource lives. So with this endpoint here, /burgers, I could get all my burgers. I can also create a new burger and add it to my existing burgers with this endpoint right here, /burgers, making sure it's a POST request to create a new one. I can also edit a singular burger. I would do so by defining the ID of that particular burger in an endpoint that I have chosen and make sure that this is a PUT HTTP request. And finally, the same for delete. I would identify the individual data by writing a URL that also has the identifier in it and make sure this is a delete HTTP request. Okay, so now that we've got that, let's get to actually using this information in practice with a tutorial. So once again on the DataStax Astra dashboard, where we can see our key spaces in the tutorial database, well, we're going to have to create a new key space. So let's go ahead and click on the Add Key Space button to the right, and then that should bring up a panel in which we can name our new key space. So I'm going to name this document so that I can show you how to work with document types. Okay, so great. If we refresh this, it should show up right here under the previous key space that we used. Now to connect to this, well, I'm just going to go to the Connect tab, and then I'm going to choose the Document API to connect to our key space. Okay? And to do this, we actually have some Swagger UI to make our life a lot easier. And to launch it, we just have to click on this URL right here. Okay, so this will launch these Swagger docs for us, and this is super helpful in letting us know what kind of commands we need to write in order to add data, get data, delete data, or edit data, okay, by simply filling out some inputs. Okay, so for example, if we want to create a collection, so in the previous tutorial, we essentially made tables. This time, instead of tables, we're going to work with collections. Okay, so replace table in your mind with a collection, and let's try it out. So there has been a default token given for us. However, if you want to use your own, so the one that you saved at the beginning of this tutorial, or if you've lost that and want to try another one, you can actually generate a new one. So if you go back here and create a new token, we're simply going to select a role. I'm going to just do admin and generate a token. So now we can use the default one, or we can use this one. So I'm going to copy that, and then back in here, delete this and just use the one we generated. You are free, however, to just keep the default if you wish. So the first input that we can put in is the namespace, or in other words, key space that we want to put our collection in. And we know that this is the NoSQL document type key space that we have just made. So in the docs, this is called namespace, but for us in DataStax Astra, it's called a key space. This is just a naming difference, so keep that in mind. And by filling in these two inputs, we are now able to write a body that will allow us to name the collection. So to do this, we need a name as a string, as the property, and the value is going to be the actual name of the collection, which again, I'm just going to choose to call pizzas. And then once we have that, I'm going to click execute. Great. So that has worked. We get a 201 response. And if we want to do this outside the Swagger UI, a request URL has been generated for us based on the inputs that we used. Okay, great. Wonderful. So we've created our collection. The next thing we need to do is add a document to this collection. So once again, let's select the correct endpoint. So there's going to be a post request to the collection that we just created by the collection ID. And let's try this out so we can populate the inputs to generate a URL for us. So once again, let's just paste in the Cassandra token. The namespace of the collection that we want to work in is called document. And the collection ID, well, we called our collection pizzas. So let's just put that in here. And now we can create our document. Okay, so let's go ahead and create our first document. I'm going to make this have a key of name and a value of pineapple pizza as a string. Okay, so there we go. We're kind of working with the same data we did before, but I'm going to show you why this way of working is different to the previous way of working in SQL in a bit. So let's go ahead and have the brand as well. So the brand of this is going to be Pizza Hut. Okay, so just like so, making sure to make all of these strings and make sure to put all the commas in the correct places too. We are also going to have a pizza ID. So once again, a pizza ID. And this time I'm just going to put some random numbers as the pizza ID, just like so. So just put in some random numbers too for this tutorial. Next, we're going to have an ingredients key. So once again, let's get up the word ingredients as a string. And this time I'm going to make an array also of text. So I'm just going to put in some text. However, you will note we are not defining that this has to be text anywhere. We are not writing a schema. Okay, we're simply putting in a document. So now after I put in some things into my ingredients, so I'm going to put pineapple, cheese, and ham, and just go ahead and click execute. You will see that has worked. Okay, we get a 201 code. The response body has generated the document ID for this JSON document, okay, in case we ever need it. And the request URL has been generated for us based on the inputs that we put in. Great. Wonderful. Okay, so now if I want to bring back all the documents in our pizza collection, I would get the get request that will search for documents in a collection. Let's once again try this out. So I'm just going to click on the try it out button, populate these inputs. So we know that the Cassandra token goes here. The namespace ID, well, we're working in the NoSQL document type namespace or key space, and the collection is called pizzas. Now, if I click execute, this will bring back the document that we put in this collection. At the moment, there is just one document. That is the document ID that got generated when we successfully put in this document into the collection. This is all under data, okay? But right now we only have one document in here. Great. Okay, so now why this is different to CQL? Well, I'm going to show you now. Let's go ahead and go back and create a new document. So here is the previous pizza that we put in, or in other words, the JSON document that we put in. Now, because we haven't defined a schema, as in we haven't said what kind of keys go in here into my object. So this time, let's just get rid of everything in here, okay, and start from scratch. And this time, I'm literally just going to have one key value pair, okay? So I'm just going to have the name of a pizza, right? Because once again, we have not defined how many key value pairs have to go in the documents that go into our pizzas collection. We literally didn't do any of that. We can put anything in our pizzas collection. So if I just simply put this and click execute, okay, so that has worked. A document ID has been generated for me. And now if I go back to getting all the documents in the pizzas collection, so once again, just go back here, making sure to use the get request and click execute, you will see that's worked. Now we have two document IDs, two documents in here, okay, but two different structures to each one. So hopefully you can see why this can be problematic. For example, if I was to be making a pizza app and decided to perhaps map the brand names onto something, the cauliflower pizza would be missing the brand name, okay? So that is just something to look out for when working with the document type. Now, not only does this apply to, the keys, but also the data types. You can put any data type under here because once again, we have not specified anything. We don't have any schema. And of course, we can also add new key value pairs. So for example, I'm just going to do this one more time. I'm going to create another new document. So let's get our post request to do this to the collection of pizzas. And I can just go ahead and add a new key value pair. This time I'm going to choose calories. So calories is the key as a string, and then the value is just going to be 200. Okay, so not a string. And if we click execute, you will see that has worked. And then if we go back and get all the documents in our pizzas collection, so once again, I'm just going to run execute, ta-da! You will see three completely different document types. There is no real sense or logic to this. We're just simply chucking stuff in there. Okay, now let's look at one of the other often used non-relational databases, the key value store. Key value databases are one of the simplest types of non-relational database. Popular examples are things like Memcache, Redis, or etcd. There is no query language native to this model to learn. It's highly similar to language level data structure, so the key value databases don't need them. Key value databases are most often used as caches, but that's not all they're good for. A creative use case fit here can win you valuable performance gains over relational models. So let's look at key value databases. They look like this. You have a key column and then you have a value column. You can actually have as many value columns as you wish. The most important thing here is that we can retrieve data back to us. So an entire row by the key, and that is the identifier in this case. Let's have a quick look at an example. Rather than switching database platforms, we can use a key value trick and implement the key value pattern, which is highly similar across databases. So let's see how to apply the key value pattern using a GraphQL API, but implemented on a wide column database, for example. Back here on our Astra DB interface, all I'm going to do is create a new key space that we can work in. Once again, I'm just going to click on the Add Key Space button. What should we call this key space? Well, let's keep in line with the previous one, so NoSQL key value type. Please go ahead and call this whatever you wish. This is what I'm choosing to call mine, and I'm just going to confirm that. Great. Now, once that has finished creating itself, I'm just going to refresh this page in order for it to show up. We can now connect to it. This time, I'm going to choose to connect our key space using the GraphQL API. Just because in the previous section we did it using the document API, I'm going to show you how to do it using the GraphQL API this time. In order to start adding a table to our key space, I'm going to have to write a mutation using GraphQL. To make our lives easier, I'm just going to go ahead and open up the playground, which will help us do all of this. Just go ahead and click on this link right here in order to open up the playground. Now, this playground will essentially help us write our queries and mutations thanks to the documentation provided that auto-generates based on what we put in the key space. To access this, we're of course going to have to put in our Cassandra token. Now, we can use the one that has been auto-generated for us, or if you wish, you can replace it with the one that you saved. So go ahead and do that, or just choose to leave the one that's there as default. The choice is up to you. Then once we have done that, we should be able to check out the docs. Just go ahead and click on the green tab, and that will bring up all the documentation that is to our disposal in order to help us write our queries and mutations. Great. The first thing we're going to do is, you guessed it, create a table. This is the mutation we need. It is a mutation, hence it's on the mutations tab, and we're going to use the mutation create table. Just go ahead and write that on the left in the playground. Now, if we click on the create table mutation in the documentation, it will tell us what we can put into our create table mutation in order to create the table. The first thing we are going to have to do is, this is required because we see a bang here, we're going to have to put in the key space name. Let's go ahead and do that. I'm just going to put the key space in the here in parenthesis. The key space that we want to work with is of course the key value key space that we created. Go ahead and put that in there as a string. The next thing we need to do here is put in the table name. This is also required, as you can see here by the bang. So go ahead and put that table name in here again as a string. We're going to choose to call it pizzas, just to be consistent with everything we've been doing so far. Next, what is also required is that we have a partition key. This functions as a key in the key value pattern we're implementing here. So once again, let's write partition key. According to the documentation, this needs to be an array. It needs to be an array, so let's go ahead and make this an array. The array needs to take a name, which is required as a string, and also a type. We're going to have to define the type that goes in here. The type, well, we actually have all these types to our disposal. It's essentially a nice cheat sheet for us, but we know that we're going to have to use the type basic of UUID because we've done this a few times already. A UUID is what we're going to have with the pizza ID. It is our choice. We can, of course, have any from the list. Great. Once we have defined our table, so we've defined exactly what the table is going to be called and what our partition key is going to be. Once again, this will function as our key in the key value scenario. we are also going to have to define some of the values that are going to go into our table, which of course play the other value role in the key value pattern. I'm going to say that our table here is going to have the value of name. The name of this is literally going to be the string name, and the type of this is just going to be text. We are going to say that our pizza table is going to have a name, and it's also going to have a brand. We're also going to have another value in here. This time I'm going to find the string brand and the type of this. The brand is also going to be the type of text. Great. Let's go ahead and see if that has worked. I'm not going to have all the same columns as we had previously because there is a lot to learn. I'm just going to show you the most basic form of creating a table using GQL or GraphQL. We're just going to run this and we should see create table true. We now know that our table has indeed been created. This is all looking fantastic. Great. Now that we have defined the schema of our table, we're going to add data to the table based on the schema. In order to do this, we actually need to change the endpoint. So what I'm going to do is just change this from GraphQL schema to GraphQL / and then my key space name. Just go ahead and do that. Let's get rid of the mutation we wrote here as well. Now, if we look in the docs, you will see the docs have been updated. This is a different endpoint and you will see that the queries have changed. We will now see the queries to get the pizzas. As well as this, you will also see the mutations have changed. Now I have a mutation in order to add a pizza to my pizzas table, delete a pizza, or update a pizza. And the bulk insert pizza into my pizzas table is also there. Wonderful. Let's go ahead and insert our first pizza. For this, again, I'm going to choose a mutation. The mutation we are going to do is insert pizzas, and then we are going to have to write this on the left. Once again, we know this is a mutation, so let's use the mutation keyword. And now let's use the insert pizzas mutation. Once again, I'm going to get up a parenthesis. Our docs are actually helping us do this because it is telling us exactly what we need to do, which fields or which values are required, and which ones aren't, and so on. Of course, the pizza ID is required, so let's go ahead and put in our pizza ID. I'm just going to put in a random unique identifier in here as a string. I'm also going to define the name as that is one of the values that we have defined in our schema. The name of my pizza is going to be pineapple pizza. Just go ahead and put that in as a string. It must be a string because we defined that it must be a string. We're also going to have a brand, which again is going to be a string. And in this case, I'm going to put Domino's. Just to check this has worked, I'm going to return some values. In fact, I'm going to return all the values. I'm going to return the pizza ID, and I'm also going to return the name and the brand. This is just the return values to see if this has worked okay and everything is working fine. We could have just returned one of the values if we wished. We have an error. This is because the pizza ID needs to be a certain format. The UUID does not take a certain format. I'm just going to generate a unique identifier online for us just to make sure the format is okay, and just copy it and paste it in here like so and click run. Great. We now know this does work because we're getting the values back. We're getting the pizza ID back, we're getting the name back, and we're also getting the brand back. This is all looking wonderful. Great. We have officially added a pizza to our pizza table. We can also update the pizza that we just added. In order to do this, once again, I'm going to write a mutation. I'm going to use the mutation keyword. We are going to use update pizzas this time. And update pizzas, well, we're going to have to update the pizza. We're going to have to search for it by its unique identifier, or in other words, the key in this key value scenario. Let's also pass through the other values we want to change. In this example, I want to change the name. I'm going to pass through the name value, and then I'm just going to change it this time to be watermelon pizza. I'm just going to put the string of watermelon pizza in here like so. If we don't put in any other values that are associated with this pizza, I'm just going to show you what happens. At the moment, I have missed out the brand, and let's just return the values of pizza ID. Once again, I'm just going to return value and then open up some curly braces and put pizza ID in. I'm also going to put the name, of course, and the brand, because those two things are the things that make up my pizza. If I click the button, you will see I've updated the pizza. I've searched for the pizza by its ID, again, your key in this key value scenario, and I've updated the name to be watermelon pizza. But because I didn't add a brand, the brand is simply null. It's as if you said, hey, you didn't put a value for the brand, so the brand is now null. Great. We are also going to have to add the brand back in. So I'm just going to go ahead and put the brand back in as a string. Domino's. That's all I'm doing. I'm putting the brand in as Domino's. Great. Now, if we click run again, you will see what our pizza looks like. Wonderful. There's one more mutation I want to show you, and that is the mutation to delete a pizza. To do this, once again, I'm going to get the mutation so we can look at the docs. I'm going to get the mutation keyword, and then I'm going to use delete pizzas. Once again, let's get up our parentheses so we can pass the value, and we want this to be the ID, so the pizza ID. I'm just going to pass through the pizza ID like so, and I'm going to paste it in. So I'm just pasting in the pizza ID that we created previously. So it's now called watermelon pizza. I'm just going to return something that we know this has worked. On this occasion, I'm just going to return back the pizza ID. That's all I'm doing. So value pizza ID. Now, if we've pressed this button, we would have deleted the pizza because the value is returning back. So we now know this has worked. Now, if I try search for the pizza by that pizza ID, I'm going to use a query this time because we're going to search for the pizza in our pizzas. I'm going to use the query keyword. Let's go ahead and get up our curly braces. I'm going to use pizzas because that is what we called our table. And then I'm going to search for the pizza by a value. We're going to have to open up some parentheses again. We're going to use value, and then we're going to use some curly braces to search for the pizza ID based on the pizza ID we want to search for. Now, I'm going to get up my curly braces and just return back some stuff so we know what is coming back to us this time when we search for the pizza by the pizza ID in the pizzas table. Once again, this time, I'm just going to put values, curly braces, and I want to return back the pizza ID of the pizza we are searching for, the name, and the brand. Just go ahead and do that and click on the play button. You will see nothing comes back. This is because we've successfully deleted the pizza with the delete pizza mutation from our pizzas table. Wonderful. This is looking good. Now I'm just going to do one more thing. Actually, I'm just going to add another pizza first. I'm going to show you that even though we are adding this data with GQL or the graph query language, it is in our database and we can actually access it however we want. We can even access it with SQL. Once again, this is some good repetition for you. I'm going to use the mutation keywords and I'm going to use the insert pizzas mutation and open up my parenthesis in order to enter the values that we want to enter for our pizza. We're going to have to give it a pizza ID, which I'm going to generate. So let's write pizza ID, and then I'm just going to generate a UUID for us later. We're also going to have the name of the pizza we want to insert. On this occasion, I'm going to say chocolate pizza because why not, as a string. We're also going to have the brand. So let's go ahead and put in a chocolate brand. So I'm going to put in Lindt. Now, we're just going to paste in our generated UUID. I just made this one up and let's return the values. I'm going to return the value of pizza ID, name, and the brand just to check that this pizza has been inserted and everything works. If we go ahead and press the play button, we will see that it has worked because the values are returning. If we now go into our AstroDB console, I want to check that this has worked using my SQL console. How do we do this? Well, again, this is a great refresher to the SQL part of this course. First off, I'm going to use the DESC keyword for describing the key spaces that live in our database. You will see there is a key space we need, so there it is. I'm going to use the keyword use in order to go into this key space, use and the key space name, followed by the semicolons to finish off the statement and hit enter. Next up, I'm going to check that the schema is the same one that we just wrote in the GraphQL playground. To do this, I'm going to use the DESC keyword for the describe keyword again. I'm going to describe the key space to see what schema live in it. Great! You will see, there it is. There is the schema I made. We've got the pizza ID, we've got the brand, and we've got the name. This is looking good. We even know that the pizza ID is the primary key. Wonderful. Now, if we select the pizzas table, so if we select everything, select keyword all, the star means all from the pizzas table, ta-da! You will see our chocolate pizza that we added using GQL. And we've got the whole table using CQL back to us, so we can view it in the CQL console. This is looking wonderful. So, can most non-relational databases and even relational databases easily be used in a key value pattern? Sure. However, databases used in this way with a key value pattern as a secondary model are different from the key value as the primary or only model, for example, like in Memcache or Redis. A key value primary system is inherently much lighter weight compared to the other models, as they have simpler or smaller footprint runtimes compared to the other non-relational databases. This is why they are so often used for low latency, high-performing cache use cases. Applying the key value pattern to, say, a tabular or wide column database could make a lot of sense. Assuming the extra functionality tabular brings over key value also makes sense for a majority of the application's codebase and use case. But there will be a limit to the number of levels deep you can nest key value pairs. When applying the key value pattern to document databases such as CouchDB and MongoDB that store entire documents in the form of JSON objects, you can think of these objects as nested key value pairs. Unlike tabular databases, you can nest key value pairs as much as you want. JSON also supports arrays and understands different data types such as strings, numbers, and Boolean values. Coming back to the true key value databases like Memcache or Redis, they're a great fit for features like leaderboards or simple data structures in an app that need to be in real time. ECTD, for example, is a well-known key value system built for housing for distributed app configuration data as a service in Kubernetes, making app or API infrastructure another great use case for the key value database. Multi-model databases are also quite popular and can perform the role of multiple NoSQL database models against a single integrated backend. Both relational and non-relational databases can be multi-model. Postgres and Cassandra Stargate provide JSON document interfaces atop relational and tabular wide columns, respectively. There are two main approaches to multi-model. You can use a polyglot database architecture or use a multi-model DBMS. Some examples here are Oracle DB offering document, graph, and RDF capabilities, making it a multi-model DBMS. Similarly, non-relational systems, Redis Key Value Store extends its application scenarios with downloadable modules into a multi-model DBMS, and Cassandra added a JSON document interface with Stargate. Some non-relational DBMS were built at inception, process different data in different shapes like Orango, OrientDB, or Cosmos DB. Now, let's finish off the course with a summary of when to use relational and/or non-relational DBMSs. While NoSQL databases have many advantages, they're not the right choice for every situation. Sometimes sticking with a tried and true SQL database is the way to go. Summing all up, here are some good reasons to use or stay with an RDBMS or relational database management system. If these are true, it may not be worth switching. Instead, augment existing apps with NoSQL. So in other words, adding microservices is a perfect opportunity. You can mix and match. People do it all the time with key value caches and RDBMSs. Try Graph for fraud detection, wide column or tabular for your app or API, or the document database for content management. However, if you know your operational database needs low latency at high load, big or unbounded datasets, global or regional deployment or replication, flexible data modeling, and high availability, as well as handling global scale at lower costs, one of the available NoSQL stores is a great choice. When you are considering migration, for example, to a wide column NoSQL store, ensure that you understand the differences between normalized and denormalized data, understand your application UI and data access layer code, build an entity relationship diagram adapting your data model, define your access patterns grouping data together wherever possible, design your primary keys and indexes, and plan deployment and move data. It's a similar story when migrating to a document database. You'll need to adapt your data model to documents, collections, fields, and more, adapt your application code, plan your deployment, and move your existing data. We've compared SQL and NoSQL databases across several factors and given you plenty of places to continue your learning. Spend the time to think about how each would apply to your data profile and use cases, and best of luck! Thanks for watching and see you again soon.